Hey everybody! So this video is going to be all about photopic vision, scotopic vision, and how the two interact to create certain perceptual effects, such as the Purkinje effect. Okay, so first, what are scotopic vision and photopic vision? Photopic vision is vision that's primarily cone-based. Now what I mean by that is that photopic vision is primarily the result of activity in your cones. Remember that cones have a lower convergence rate. And if you remember what convergence is, that's basically how many receptors converge on one ganglion. So cones have a lower convergence rate, meaning fewer cones converge on a single ganglion than rods. More rods converge on a single ganglion. Now what that means is if you have an equal amount of light hitting both cones and rods, more rods receiving that input are going to feed in to a single cone. So, for example, let's imagine that we have two ganglion cells. I know the lines, stick with me on this one. Now, on one, it's only receiving information from rods. So I'm going to put a little R's on here. Ta-da! And the other only receives input from cones. But remember that cones have a lower convergence rate. So there are fewer cones converging on a single ganglion than rods do. All right? So fewer cones going into this one ganglion than there are rods going into this one. All right? Now, let's again imagine that one light source is hitting all of these receptors, all of them, and it's giving them 1 unit of light for each one. All right? So this has to be a remarkably dim light so that it's only giving 1 unit of light. Now let's imagine that in order for each of these ganglions to achieve an action potential, so to become excited, to send a signal onto your brain, they have to receive the equivalent of the activity necessary to cause the equivalent to the activity caused by 5 units. So both of them need 5. Well, the same light source that's coming in and illuminating or activating all of these receptors with only 1 unit of light is going to activate this ganglion because it's, how many did I write? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's getting 9 units. So this ganglion, with this very dim light, is going to become active. This one won't, because it's only receiving 3. In order for this ganglion to become active, each of these numbers would have to become higher. So instead of 1, they'd all have to be 2s. All right, now that ganglion will fire. So this is an example of how that convergence rate that cones and rods differ in can make cones, or rods rather, more sensitive to light, meaning they don't need as much light to become active. Now, let's go back to photopic and scotopic vision. Photopic vision, as I said, is cone-based vision. So it's vision that's primarily reliant on your cones. Scotopic vision is rod-based vision. So it's vision primarily based on your on activity in your rods. Now, for the majority of our day, you know, we're either outside or in well-lit rooms, so the illumination is high enough that both our rods and cones are active. In these circumstances, I'm going to try and share the screen with you. In these situations, both, so, you know, moderate illumination, in these situations, both photopic vision and scotopic vision are co-occurring. So the majority of the day, both your rods and your cones are currently active, or concurrently active. All right? However, if illumination gets really bright, your scotopic vision doesn't happen anymore, mainly because your rods become oversaturated. They become fatigued. Whereas in extremely low levels of light, your photopic vision doesn't work as well because, again, there's not as much illumination. There's not, so you remember back in the example here, when illumination gets low enough that the ganglions that are innervated by cones don't get activated. So in low levels of light, you primarily rely on scotopic vision. But in most levels of light, moderate and higher, most of the day that you are awake, most of the day, unless you're hanging out in dark rooms or something, most of the day, you're using both photopic and scotopic vision, meaning both rods and cones are being are responsible for your vision. But at low levels, again, only your rods are active, and so you're primarily using scotopic vision. Now, what this causes is it changes how intense some wavelengths look to us. So if we look at, if we're in moderate or high light, then we're using primarily photopic vision. And your cones respond to a different set of wavelengths differently than your rods do. So here, I'm going to try and share it with you again. Here you see the absorption spectrums, or the spectral sensitivities of both photopic vision, so your cones, and scotopic vision, so your rods. You'll notice that your cones are sensitive to longer wavelengths, whereas your rods are sensitive to lower wavelengths. So what happens is that in your moderate and high levels of illumination, your longer wavelengths, like your reds and your yellows, are going to seem brighter because, let's say, you have 10 units of red wavelength light coming at your eyes. I know I'm combining terms. Red is a perceptual effect. Wavelength is a physical aspect of the wavelength. But stick with me on this. I'm trying to make it a little simpler. So let's imagine that you're in moderate and high levels of illumination, so you're primarily using photopic vision, and 10 units of long wavelength or red light is coming into your eyes. Well, that 10 units is going to seem fairly high because your cones are reacting to it, and they react to it better than and they react to it well. But as illumination drops and you shift from photopic vision to scotopic vision, those same 10 units of long wavelength red light won't activate your rods to the same extent, largely because of the differences in spectral sensitivity. So you see up here where red is, your rods don't respond basically at all. Only your cones do. But again, when illumination is low, your cones don't react as well. So when illumination is low, red seems dull. Now, really, when illumination is low and we shift all the way over to scotopic vision, we don't see colors at all. What we see is everything basically in some shade of gray. So that long wavelength red light would seem like a very dull gray. However, your shorter wavelengths, like your blues and your violets and even your greens, because your rods, which are the basis of your scotopic vision, are primarily being used, 10 units of blue or violet light or short wavelength light will really activate your rods, and so they'll seem more intense. And so again, it won't, because you're primarily using your rods, it won't look blue, it won't look violet, it'll look gray, but that gray will be brighter. All right, so this effect where we see a shifting in well, I guess before I talk about the shift, so we've talked about well, let me unshow this. So in moderate and high wavelengths or levels of illumination, in moderate and high levels of illumination, you've got primarily photopic vision. And your cones, which are the basis of photopic vision, are really responsive to long wave, or more responsive to long wavelengths, like reds and yellows. All right, and so if you're hanging out in a well-lit place, your reds and your yellows are probably going to seem more intense. Whereas your blues probably aren't going to seem as bright. They're not going to seem as intense. They're not going to seem as vibrant. Okay, but as you shift, so as illumination declines, so let's say it starts getting really dark outside, all right? You don't have a flashlight or something. Well, regardless, it gets dark outside. As illumination declines, you shift from photopic vision to scotopic vision, which also causes a shift in the perceivable vibrance or intensity or brightness of your long wavelength colors, reds and yellows, and your short wavelength colors, blues and violets. In moderate and high wavelength, when you're using photopic vision, your reds, your yellows, your long wavelength colors, they seem more vibrant because they're really activating your cones, the basis of your photopic system. But as you move into low levels of illumination, now your blues and violets are more intense or more bright, because now you're using scotopic vision, which is based on activity in your rods. So, your rods, again, respond to short wavelength light, or blues and violets. So this shift in the relative intensity of colors when moving from high levels of illumination to low levels of illumination is called the Purkinje effect. And it's dependent upon shifting from using both photopic and scotopic vision to using only scotopic vision. So, brief review. Photopic vision primarily uses your cones. Your cones are primarily responsive, or are more responsive to long wavelengths, or at least they're more responsive than your rods are. So reds and yellows and your long wavelength colors seem more vibrant when photopic vision is involved. Scotopic vision, on the other hand, is rod-based, and your rods are more sensitive to short wavelength colors, like blues and violets. So when illumination is low, and so your cones aren't working anymore, and so you're only using your rods, you are only using scotopic vision. And at this point, blues and violets seem more vibrant. Now, one tripping point here, and I've mentioned it already, is people might think, well, I thought you can't see colors when you're with your rods. And that's right, you can't. So the Purkinje effect isn't really a shift from reds and yellows seeming more vibrant as reds and yellows to seeming like dull reds and yellows, and your blues shifting from dull blues to vibrant blues. No, what happens is you have your bright reds and yellows and your dull blues, but then when illumination gets low, they switch. But you don't see them as colors anymore. You see them as shades of gray. So now your reds and yellows seem like dull grays, and your blues seem like bright grays. All right. I hope that helps clear up the differences between photopic and scotopic vision, and I hope that helps understand the Purkinje effect. It's a really neat effect. Hopefully sometime you can spend a little time outside and check it out. It's kind of cool. In the past, because I don't get home till late and I have to mow a lawn, you really see it in the greens. Suddenly there's a moment around dusk or a little after where the greens just boom. Suddenly the trees and the grass is really green. But that's the Purkinje effect. And it's because of the shifting from primarily photopic vision to scotopic vision. All right. Again, if you have any questions, please let me know. Send them my way. Other than that, I hope this video has been helpful, and I'll see everybody later on.